On July 1st, 2025, the Atlas survey system in Hawaii reported a new object moving on a trajectory that didn't match the typical patterns of comets or near-Earth asteroids. Within weeks, preliminary orbital models suggested that it may have entered the solar system from beyond it, raising the possibility that this could be an interstellar visitor. That idea alone captured immediate scientific interest. But what began as a routine classification effort has turned more complicated. The object's brightness and activity patterns are not behaving as expected, and researchers are now working to understand what could be driving these unusual changes. If you're interested in following along as this situation develops in real time, feel free to subscribe because right now, as of November 2025, astronomers are monitoring this object with increased attention, alongside many other active targets in the sky. Let's clarify what we currently understand, because the context matters. The object has been discussed as a potential interstellar candidate, but it has not been officially designated as 3I. The numbering only becomes official after a formal confirmation of interstellar origin from the Minor Planet Center. For comparison, the first confirmed interstellar object was Oumuamua in 2017, and the second was 2I Borisov in 2019. If this object were eventually confirmed as interstellar, then it would join that very small category. Early photometric estimates suggested it might be relatively large compared to many short-period comets, though those estimates remain uncertain because brightness does not directly translate to size when activity levels are unknown. The proposed interstellar interpretation comes from early orbital solutions that indicated a slightly hyperbolic trajectory. However, hyperbolic paths can also result from observational uncertainty or gravitational interactions, so researchers are still refining the orbit. If the trajectory ultimately proves to be hyperbolic with a clear excess velocity, that would indicate an origin outside the solar system. But confirmation requires time, more data, and careful analysis, not assumptions. What drew attention early on was the possible orbit. Preliminary solutions suggested the object might be moving on a high inclination, potentially retrograde path, meaning its motion could run opposite to the general direction of the planets and most long-term stable bodies in the solar system. If you picture the solar system as a broad rotating disk where most objects move counterclockwise when viewed from above, a retrograde object would cut through that disk moving clockwise instead. Some early estimates placed the inclination near 170 degrees or higher, which would be extremely tilted relative to the solar system's plane. However, this measurement is still being refined as new data improves the orbit calculation. And here's where early analysis became especially interesting. The preliminary orbit solutions didn't just suggest a possible retrograde path. They also indicated that 3I Atlas might be traveling close to the ecliptic plane, the same broad disk where the planets orbit. If that configuration holds as the orbit is refined, it would be statistically unusual. Dr. Avi Loeb and others have noted that an interstellar object arriving with a retrograde trajectory near the ecliptic would be rare, with rough estimates placing the probability at well under 1%. That doesn't imply anything exotic, but it does make the geometry worth paying attention to as more data comes in. Through July, August, and September 2025, observations showed behavior consistent with a small interstellar comet approaching the Sun. Outgassing became visible as warming released volatile materials, forming a coma of dust and gas. The brightness varied in a pattern that made sense for a rotating, irregular object, becoming more active near perihelion, its closest point to the Sun. Then something unexpected happened. As telescopes gathered higher resolution imagery and more precise photometry, the estimated size changed dramatically. What early brightness readings suggested might be a 10 to 20 kilometer nucleus was later revised downward to a diameter likely under 1 kilometer, with estimates ranging from roughly 400 meters to a few kilometers at most. A large interstellar comet suddenly became a small one, forcing researchers to rethink how it was producing the level of activity that had already been observed. Here's why that matters. The object was already showing noticeable activity, releasing dust and gas as it warmed. Early modeling suggested that the rate of material leaving the surface could be substantial. If 3I Atlas were a 10-kilometer object, that level of activity would be significant, though broadly consistent with what we see in large comets. But if the nucleus is actually under a kilometer in size, then that same activity represents a much higher fraction of its total mass being shed. As the object moved through perihelion, its closest approach to the Sun, Its brightness increased and the visible outgassing intensified, which is expected for an active comet. The surprise came after perihelion. Observers began detecting what astronomers call non-gravitational acceleration, tiny deviations from the predicted gravitational trajectory caused by jets of material pushing the nucleus as they escape into space. These accelerations can be measured with high precision, and they allow researchers to estimate how much mass is being lost. Some independent analyses, including work discussed by Dr. Avi Loeb, suggest that if the nucleus is on the smaller end of the estimated size range, then the total mass lost over the observed period could be a notably large fraction of the object's mass. For a nucleus only a few hundred meters across, losing even several percent of its mass in months would be extraordinary. That's why the size estimate matters so much. The smaller the nucleus, the more dramatic the implied mass loss becomes. This is where the main physics question appears. Using standard models for comet behavior, a nucleus only a few hundred meters across at this distance from the Sun should not be losing mass at such a high rate. The relationship between solar heating, ice sublimation, and the force of escaping material has been studied for decades. Yet, if the smaller size estimates for 3I Atlas are correct, the apparent activity level seems higher than those models would normally predict. A few explanations are being discussed, and each has complications. One possibility is that the size has been underestimated. If the nucleus is closer to the several kilometer end of the current uncertainty range, then the implied mass loss becomes much less extreme. That scenario would require the surface to be unusually dark, reflecting very little light. Some interstellar objects could plausibly carry carbon-rich or space-weathered surfaces that make them appear smaller than they are when measured by brightness alone. But adjusting the size upward does not fully resolve the behavior that's being observed. That's why many researchers are now considering fragmentation as a likely factor. In this scenario, 3I Atlas is not a single intact body, but one that is beginning to break apart. There is precedent. The interstellar comet 2I Borisov showed indications of fragmentation during its passage. And many solar system comets are known to split when internal pressure from heating exceeds their structural strength. If 3I Atlas has fractured recently, newly exposed interior material, rich in volatile ices, could drive stronger outgassing than the weathered surface alone. That would naturally produce elevated activity levels without requiring exotic explanations. And this is where the story becomes especially compelling. Recent observations in early November 2025, including processed images shared by experienced observers such as Michael Niebling and Gerald Buckner of the British Astronomical Association, show multiple distinct jet-like structures extending from 3I Atlas. And not just one or two. Some reports describe 6 or more narrow directional streams of material, rather than the smooth, diffuse coma seen earlier in the year. Preliminary measurements based on these images suggest a primary tail stretching on the order of millions of kilometers, with additional structures extending in the opposite direction. These numbers vary depending on the imaging technique, but the scale appears genuinely large. If the nucleus has recently begun to fracture, these jets could correspond to newly exposed areas venting fresh, volatile material. Fragmentation events often occur near perihelion, when heating is strongest, so the timing would be consistent with that scenario. But there's a puzzle. If the breakup were already well underway, we would expect the fragments to separate visibly over time. So far, observations still show a relatively compact central region. That suggests the fragmentation may be extremely recent, gradual, or occurring internally, with only partial separation so far. Now, stepping back to the orbit for context, the retrograde motion by itself is not unusual. For interstellar visitors, prograde and retrograde orbits are roughly equally likely, since they approach from all directions. What makes 3I Atlas interesting is how these orbital dynamics, the activity levels, and the possible fragmentation signs all converge into a single object that is still undergoing rapid observational revision in real time. But the ecliptic alignment is a separate point. The ecliptic plane represents only a very narrow band of possible arrival angles in the sky. An interstellar object could enter the solar system from almost any direction, at almost any inclination. So the probability of an object arriving on a path this closely aligned with the ecliptic is statistically very small. The estimated likelihood is around 0.2%. In other words, if you had a random sample of around 500 interstellar visitors, you might expect to see this configuration roughly once. Of course, with only 3 confirmed interstellar objects so far, we do not yet have enough data to determine what the true distribution of arrival angles looks like. There may be mechanisms in how objects are ejected from their parent systems that create certain biases, or 3I Atlas may simply represent a low probability trajectory that happened by chance. Still, when viewed alongside the unusual activity levels, the ongoing mass loss, and the possible fragmentation scenario, the orbital configuration adds another factor of interest. It does not confirm any extraordinary explanation on its own. It simply highlights that this object is particularly worth studying in detail. So what are the next steps? What observations are underway, and what could they reveal? The James Webb Space Telescope observed 3I Atlas on August 6, 2025, using infrared measurements to analyze thermal emission from the nucleus. These data may provide a more reliable size estimate, independent of reflectivity assumptions, and could also show whether multiple heat sources are present if fragmentation is occurring. The analysis of these observations is ongoing. Webb could not continue observing the object between August 25th and December 9th, 2025 because of solar alignment constraints. But additional observations may resume in late December as visibility improves. In addition, the European Space Agency's JUICE spacecraft, currently en route to Jupiter, has been observing 3I Atlas during November 2025. Because JUICE transmits data slowly from its current distance, the full dataset is expected to be available in February 2026. These observations will offer a viewing geometry entirely different from Earth-based telescopes and Hubble, which may clarify structural details. Lastly, on December 19, 2025, the object will reach its closest approach to Earth at approximately 1.8 AU, around 270 million kilometers. While still far, this distance is favorable enough that several observatories have scheduled coordinated campaigns during this window to capture as much high-quality data as possible. The key question moving forward is whether 3I Atlas maintains its current level of activity as it travels farther from the Sun. If the elevated activity continues, that would be unusual and could support the idea that fragmentation has recently exposed fresh volatile material. On the other hand, if the activity decreases in a typical post-perihelion pattern, the recent jet formations may have been a short-lived outburst rather than evidence of ongoing structural breakup. At the moment, with 7 or more active jets and a brightness pattern that has intensified instead of declining, 3I Atlas is not following the standard trend seen in most comets after perihelion. It's also important to address a pattern that appears whenever an interstellar object shows unexpected behavior. Speculation often turns toward non-natural explanations. Some have suggested that the jet directions resemble propulsion, or that the orbital alignment is too precise to be natural. However, the current data does not support those interpretations. Everything observed so far is consistent with a natural cometary body. The jets appear irregular and consistent with volatile outgassing. The trajectory corresponds to a standard gravitational orbit, with no deviations that would suggest external control. Spectroscopic observations so far show typical comet-like compounds, including water vapor, dust, and organic material. The orbital configuration is statistically uncommon, but not outside the range of natural variation. These observations matter not because they suggest something extraordinary, but because they challenge current models. When an object behaves differently than expected, it lets researchers adjust assumptions, update thermal and structural models, and better understand how interstellar material reacts to solar heating. Progress happens when data and predictions do not perfectly match. The most likely explanation for 3I Atlas is simple. It is likely a fragmenting interstellar comet whose size was overestimated early on. That initial assumption makes the current mass loss look more dramatic than it is. As measurements improve, the apparent discrepancy may resolve. The retrograde orbit is unusual, but unusual is not the same as unnatural. The jets, while striking, still fit with normal cometary behavior under heat stress. What makes this moment interesting is that the data is still developing. The James Webb observations from August are still being processed, and the December observation window has not yet occurred. The comet remains active enough for models to continue being refined in real time. Astronomers are watching closely not because they expect something dramatic, but because objects like this help refine how we understand material formed around other stars. Whether 3I Atlas turns out to behave like a typical comet or shows something new, both outcomes add to our knowledge of interstellar objects. The next major updates are expected in late December 2025 during closest approach, and again in February 2026 when JUICE data is available. Observations will continue as long as the comet remains bright enough to track. What do you think best explains the current mass loss? A size miscalculation, active fragmentation, or something about interstellar material we haven't modeled yet? Share your thoughts in the comments and consider subscribing to follow the December updates. Thank you for watching and see you in the next video.